Hey folks, welcome back to Advent of Code in F#. We're at day 14, part 2 today. We ended last video when I solved part 1. It's the one with the marbles and the labyrinths, and we have to tilt the labyrinth and figure out what the load is on the north support beam, that one. And I saw part 2 at the end of the stream, and I was like, oh no, that sounds like a lot more work. But actually it was pretty okay. So let's take a look at how I solved part 2 for day 14. I did record my video, but I was fighting with off-by-one errors for about an hour, and I want to spare you the details, so I'm just going to provide a quick recap. So for part 1, we had to do one single tilt of our marble labyrinth, tilt it north, and then count the load on the north support beam. So we basically had to do only one single step. And in part 2, we are running cycles, spin cycles, which is doing a tilt north, west, south, east. That's one single cycle. And we had to do 1 billion cycles and then figure out the total load on the north support beam. This is a crazy big number. So this is hinting at you don't need to do it 1 billion times. And one way to figure out quickly whether or not you have to do stuff a billion of times is getting a feeling with the problem, with the search space, the solution space, like, is there a potential for cycles here? And there definitely is. And how you can figure it out pretty easily is with something called the pigeonhole principle. And it states that if you have n pigeons and you have m pigeonholes, and you have more pigeons than you have pigeonholes, and you put every pigeon in a hole, there is definitely one pigeonhole with more than one pigeon. That's a lot of pigeons. But the example or the principle is like a way to get an intuition of, will I have hash collisions, or will I have a problem with containers that will contain more than one element? And for today, we can take a look at, we have 1 billion cycles, and we have only a limited amount of possible spaces or states, different states. So if I take a look at my input, for example, which is a 100 by 100 matrix. Yes, so it's 10,000 elements, and every element can be empty or a wall or a rock. The space is a bit smaller because the walls don't move, but for sake of simplicity, let's say that we have 3 different states in each of those 10,000, so that is 30,000 different states we can have in our grid. And if those different states are like the pigeonholes, and our number of cycles, which can run up to 1 billion, are different pigeons, there are definitely more pigeons than pigeonholes, so we definitely will encounter cycles. So that's how I convinced myself, at least, that looking for cycles might be a good approach for today. And turns out it did, so let's take a look at how we solved part 2. It's the same code as part 1, even with the... what was it? Oh yeah, my copy pasting of 2D arrays. I did not do inline updates, and I was a bit concerned about the performance. Rightly so, it turns out. Let's quickly go to my timings here. So I just did some back of the napkin benchmarking, and using my copy pasting of 2D matrices, it took 1.5 minutes to find my cycle. And if I changed my algorithm to use just mutable 2D matrices, it's a bit harder to detect the cycle than if you don't have different versions of your matrix, but you can calculate a hash or stringify your matrix, stuff like that. And then it took my computer almost half the time. So yes, copy pasting arrays is expensive. But doable for today. So how did I solve part 2? Two-parter. I found cycles, and I did full cycles, or I found loops, sorry, and I did full cycles instead of only tilting north. So let's take a look at how I did tilting east, south, and west first. And I did it very basic. I just rotate my matrix in between tilts. So when I tilt north, I rotate my matrix 90 degrees clockwise, and then I tilt north again, and that is exactly the same as tilting west, I guess. So that's how I do my tilts in the different directions. I just rotate my matrix every time. And in order to rotate my matrix, I don't do any crazy matrix multiplication, sine, cosine things. I just use our trusty old array2d init function. And this is the function that initializes the new array, and it just flips around rows and columns. So we get a 90-degree clockwise rotated matrix. I had to draw a lot on a whiteboard to figure out this, this indexing magic. But I even wrote some tests for a change. So this is how I rotate a matrix. Parsing is the same. Tilting north is exactly the same, unchanged. And this is where part 2 starts. So if I have my tilting north logic and I have my rotation logic, my matrix rotation, I can do a full cycle by just tilting north, rotating, tilting north, rotating. And this is tilting in all 4 directions. And at the end, my matrix ends up in the north is up fashion again. So we are ready for another cycle. So implementing cycle was easier than I expected. Once I figured out I could just rotate my platform. Next part for part 2 is figuring out where my loop was. That was actually the part where I lost the better part of an hour, because in my head, if I was going to find a loop, I would loop back to the first or the initial state of the platform. So I could find a loop that just has the same state as my initial input. Apparently that was not the case. So I have some states in front, and then I have a loop, and the loop never refers to the initial states before the loop, and that was super confusing. I did not figure that out for a long time. So if you look at this logic, what is it doing? It's a recursive function, and it takes a set of visited states, or it's not a set, but I started out with a set, but I made it a bit more complicated. The current cycle number and the current platform state. And I just run one cycle, so that's tilting the 4 directions here. And then I try to figure out, have we seen this exact state before? If we have found a loop. Then we need to figure out stuff like how long was the loop, what was before the loop, stuff like that. And if we have not found a loop, we can recursively continue with the next state of the platform, the next cycle count, and an updated set of visited states. What is this NY stuff? The easiest way to explain is taking a look at the recursive call here. So when I build my visited set, I keep track of the state. So next is the next state we calculated, so one full cycle of the platform. And then I say, okay, we found it at cycle number n+1. Yeah, and that's it. And in our recursive call, we take a look at, is there a state in there in our visited set that already contains the newly found cycle or the newly found platform state? If there is, then we return stuff. And this is where it got tricky for me. We return the platform state, again, because the initial state does not have to be the start of the cycle. So we need to keep track of the last state we found when we detect the cycle. And then these 2 magical indices, which are like single letter, very badly named things. But this is the... what is it? This was the start of the cycle I. So let's maybe call it that. So that's the platform. And that's the cycle start. So this is the start of the cycle. And n is the current cycle number. So I return the last state of the platform when we detected a cycle, and then I say, this is how long the cycle actually is. So this part will keep repeating. And oh, by the way, the cycle started at this cycle, or the loop started at this cycle. I'm confusing myself with all this loop and cycle confusion. So let's keep cycle for cycle, and let's call our loop detection loop. Something like this. So yeah, the fact that the cycle did not have to start or does never have to return to the initial state was very confusing for me, and it took me the better part of an hour. But once I figured that out, things run smoothly. And then I have this little helper function that runs cycle a certain amount of times on a given platform, so we can do the rest of the cycles after the cycle. Find load is still the same as it was for part 1. That's just doing some summing and multiplication. And this is the meat of the matter. This is our part 2 solver. We, again, just parse our input into a 2D array. Then we find our loop, given our initial platform and the initial set of visited states. And it returns the final platform state. So once we found a cycle, we also return the platform as it was at the end of the cycle. We return the length of the cycle, or the length of the loop, sorry, and we return where the loop started. And with all those numbers, we can calculate how many more times we have to run a cycle. So it's 1 billion minus the loop start, because the fiddly end before the loop, we did that once, we don't have to repeat that. And then we figure out how many times we have to, we know how many loops we ran, so we can figure out how many cycles we need to run after all those loops. I don't even care how many loops we have to iterate to reach 1 billion. And then we just run our cycles that many times on that platform after we visited the loop, and we calculate the load. So yeah, it was a pretty fun puzzle for me. I learned a lot about myself again, about my impatience and off by one bug things. I always have bugs in things. That's maybe why I don't like Array 2D as much as I should. The room for off by one bugs is so huge, and I'm so notoriously bad at them, even with tests. It's crazy. Yeah, but I really like the puzzle. What I learned was rotate a matrix. You can do it with matrix multiplication, but you can also do it with just this init thing and figuring out where we have to look in the original matrix to build a new matrix. So that was a cool insight I gained. I learned that copy-pasting matrices is indeed a lot slower than just updating them mutably. And once I did the mutable thing, my program suddenly had a lot of bugs because a lot of the code does not take that mutability into account. So I had to rebuild my loop detection to work with mutable matrices. For example, if you put stuff in a list or a set and you compare with them, or you see like, did we meet them before? Yeah, if the matrix changes underneath you, this approach does not work. So I had to hash the matrix and put that in a visited set. So it was all kinds of weird. And that's why mutability is something to be very aware of, especially if you're writing a lot of code that like does not care about mutability or pretends that mutability does not exist. So that was like interesting fact number 2 for me. And other than that, it was a great puzzle, and it was a real CPU burner, even with the mutable updates. So this is a really slow solve. If you have an approach that solved it sub-second or that solved it really fast, please let me know how you did it, because I would not know how I would speed up this by like a factor of 10 or an order of magnitude. That's all I have for day 14, part 2. And I hope to see you again next time on Advent of Code in F#. Bye-bye.